Hey, how y'all doing?
Good, how are you?
Doing pretty well. Let's think. Oh yeah, a couple administrative things first. Then maybe cute questions and answers from you about administrative sort of matters. Then questions on the ANOVA sort of lab content and homework, and then move forward into regression. Uh, so it's week 2, which means that seems early for a test, but this is one of those 5-week classes. So at the end of this week, including the Thursday class, we're 40% done with the entire term. So yeah, maybe it's about right for an exam. By tomorrow, I'm going to check to verify that the questions that I think are already online, the sample exam questions, are the ones I want you to look at. And you could view those as like the questions that I would ask a regular group of Stat 313 students who are taking the test in a classroom. Now, of course, you're not going to be doing that. You're going to be doing it via the online world, but that's okay. The questions that are there are the sort that I like to ask. And you can just imagine what if your questions were about the same, except for instead of writing out your answer by hand, you type your answer in a little box. Now, this does make a couple things different for a class taking a test. One of those huge differences that I want to draw your attention to is probably I don't want you to spend any time trying to use Canvas's typesetting package to write mu1 equals mu2 equals mu3 equals mu4. That's a lot of wasted time. And what I want to do is set it up such that you can write your answers out on paper if you'd like to, and then just upload the piece of paper. If for whatever reason you just type in that little box, see my piece of paper, just be sure to label the paper correctly, and I'll let you scan it or take a picture with your phone and upload that, and it's all good. So the test is meant to be one where a student could answer all the questions completely correctly without opening the software and without using any data sets provided. But it's also one where if you wanted to use the data sets and the software a lot, that would be absolutely fine by me. A lot of different students who taken both extremes, and both extremes allow a student to do just fine. Just know that every question is one that could be answered without even using the data sets. So that will give you some clues about maybe an approach to an answer, even if you wanted to use the data. Similarly, if you do use the data set, you should think, am I producing an analysis really, really different than the one that's provided to me? Because if you're producing something dramatically different than what was already provided to you, it sounds like you might be going down the wrong path conceptually relative to what would allow you to do quite well on the final exam, the first exam. So by Wednesday, everything should be perfect in terms of the sample exam questions. I'd like to spend an hour in class on Thursday going over those sample exam questions. And then the exam will be open for you right following class on Thursday. You can take it as soon as I guess this is 4 to 5. You can take it as soon as 5 p.m. on Thursday if you'd like, but you're welcome to get it done anytime as long as you are finished by 11:59 on Friday. So figure out what works best for you. Last two things. One of them is I suggest always students create a cheat sheet for the exam, even if you're being given access to everything that's on Canvas. And even if you're being given access to the whole of the internet, which by the way is useless, just write down the most important equations and definitions as you think they might be likely to appear on a test. And you can key off of those often much, much quicker than if you try to use the textbook or the internet, trying to search for just that one factoid. So pre-preparing by studying as if you will not have access to these other things is a great way to sort of get towards the material. Okay, so that's the last two things I want to mention. Any questions about administrative things in general or the test coming up?
Is the test going to be timed, or is it just we can start Thursday and then we have until Friday?
Great question. I thought all tests were timed, but maybe there is a feature that would allow me to set it as untimed. I just had planned on a 50-minute timed test. And so be sure that when you sit down ready to take it, that you've got, well, your snacks in front of you and you're good to go. It is admittedly, I think a test that could easily be done in 50 minutes, but most students like to spend the whole time. And most students find that the timed exams, exam 1 and 2, are a bit harder to score points on than the final exam at the end of the term, where you have more time per question. Okay. On the last exams, I'll have like 2 parts, final exam A, final exam B, if you will. You might want to think about that way. And each of them are meant to be a 50-minute test, but I'll give you 75 for each of those. So students who feel rushed for time, and you'll find out soon whether you're in that category or not. Don't worry about the final exam. The final exam scores always could be considerably higher than the earlier test scores for the students who work slowly. Great question. Thanks for asking. Someone else?
Where are the sample exams going to be when you do end up posting them?
They'll probably be on the main page for the class, and it'll just be where it says sample exams for exam 1. And then I will provide the answers to those by Thursday morning. And you should then look over my sample exam answers and then ask questions Thursday during class time. And I think that's good. Also, questions related to anything are great for Thursday class time. Also, the homework that will be assigned on Wednesday, I know that the homework will be due not really at a convenient time for you relative to the exam, but I have yet to think about whether I want to make the answers available for that one. Maybe if you show up in class on Thursday and just ask directly about how to do the homework, maybe that'd be the best place to go. Okay, so we'll decide that one later. Last call for administrative questions.
I don't know if I missed this because I came in like 2 minutes late, but do you have office hours tomorrow?
Yeah, the standard times. And I don't remember when those are, but in Canvas, it sort of should give you a direct link and just click your way in during any of those time slots. And yeah, I will let you all know I will let you know in advance, if at all possible, if I'm going to be unable to make one of those office hours. And I would try and reschedule it, but I don't have any plans of doing that between now and the end of the term. But stuff happens, that emergency thing that comes up. I'll let you know if that's going to be necessary. Probably not. Okay, so how about questions from the more recent class material? In ANOVA, I guess more recently, you checked the conditions, whether the ANOVA conditions are met. There's a normality in the residuals is the best way to go, and equality of spread. And I guess in addition to checking those things, the lab also walked you through a situation where you compared the individual group means to each other after the fact, post hoc, after the hypothesis test that says not all the means are the same. What do? Well, do one of those post hoc comparison procedures and tell me which means are different than which other ones. So that's a nice way of tackling the natural question that follows the hypothesis test. Not always do people do the post hoc following, but almost always would you do the post hoc test after the regular hypothesis test. Okay, questions about any of the ANOVA content? Okay, so what I'm going to do is open up a screen, or I guess share a screen from, I guess, desktop 1, share. And we're going to move in on new material. But that, when I say new material, what I really mean is material we haven't formally covered yet in Stat 313. A lot of you have seen the content in what we're doing today in a prior class. Not every one of you in your 218 class did a lot with regression. Some of you did a fair amount of regression, depending on the term that you took 218 or comparable. Some of you, based on your background, have done no regression at all. Most of you a little bit. Some of you maybe zero. So review for most people. And then I think that sets us up nicely for Wednesday, the first new thing of the entire term that should be new to all of you and still very doable before the exam on Friday or Thursday, Friday. Okay. So regression really, it's just used to see if there's a relationship, and in particular, a linear relationship between some quantitative explanatory variable and a quantitative response variable. In terms of the analyses that we've done so far this term, you've looked at the dioecious trees in a couple different ways. Even on the first homework set, I sort of drew in two lines showing that for the M's and the F's, the average number of flowers seems to depend on DBH. Well, maybe we could predict then the number of flowers based on the diameter of the tree at breast height, DBH. Okay. Let me show you another example, and I'll show you with this concept of a graph of means. Now, where's my example? Oh, okay, so I've got data here on homes that sold in the city of San Luis Obispo in the year 1998. Now, you might be thinking that was a long time ago, and in fact, you're right. But the home prices are in the one column here, and the size of the home in hundreds of square feet. So like 17.05 times 100, that'd be 1,750 square feet. Okay, so 1,705 square feet. Okay, so 1594 is 1,594 square feet. So maybe it's not the unit the way you'd write it out, but still it's not uncommon. And price in dollars may depend on home size. And as we've found this term, analyze fit y by x really does everything we need until Wednesday. But Wednesday, we're going to switch over to, analyze fit model, and everything's going to work just like before. It'll look a little bit different, but everything we've already done will work just fine with analyze fit model. But we'll be able to do a whole lot more things. But for now, fit y by x seems to still work, so let's go with it. So question that makes sense to me is, does the price of a home depend on the size of the home? Or perhaps, how does the price of the home depend upon the size of the home? I click OK. We get to this big old graph, and in this scatter plot, I want to look at this thing that I would call the graph of averages. And I'm going to make it bigger here so we can look at it a little bit more carefully. So I'm thinking I could, for the different homes, I could chunk them out into small homes in terms of the square footage, medium, large, very large, a lot of different sized homes out there. And so let's go with homes that are under, say, 1,200 square feet, 1,200 to 1,600 square feet. I wish I could draw vertical lines better. I'm sorry. 1,600 to 2,000, 2,000 to 2,400, 2,400. Let's go to 3,000. It's a little bit wider of a category. And actually, let's even remove that last category. Let's just say 2,400 to 3,000, and then above 3,000. Now, if in each of these vertical categories, we could do something like an ANOVA. Are you in category small, small to medium, medium, large, or very large? Based on the size of the home, I guess you could say the size category could be used to predict the average. And it seems to me that the average does increase across these categories. I'm suggesting that if we were to find the average price in the small homes, I'm just going to plot it right there. And you're thinking that seems a little bit above all of them, except for there are those two up here that you might have missed. So I'm gonna go back and remove the little dots. Come on. Okay, good. So in the small to medium homes, I'm gonna say the average is there-ish. Again, the skew right nature of the price does tend to pull the mean up from where the middle seems to be. Medium-sized homes, large homes, and then the very large home, the average price seems to be there. Okay, that's, if you will, a graph of averages. And if I wanted to use that as a method of predicting the price of homes, I can probably just connect the dots. And a reasonable method of predicting the price of a home based on the size of the home seems apparent. Any questions about the concept of a graph of averages? Okay, so I'm going to clear that and move forward. So with that graph of averages or graph of means, if it was straight line-ish or linear, we could possibly use the method that we call regression. Let me mention a bit about the history of regression. Have y'all heard of Ceres, the asteroid, CERES? I'm looking at the screen and I'm not seeing anyone nodding. Have you heard of a Ceres, anyone? Okay, this is where the in class is like a whole lot better because like there's always like 2 students of the 20 that are nodding. Okay, look it up on the internet, it's a thing, okay? Ceres is well known as an asteroid because it comes down with some regularity, but it's also well known among statisticians because this guy named Gauss, Carl Friedrich Gauss, mathematician you might have heard of, he invented a statistical method in the 1890s, and some 10 years after he invented the statistical method to tackle a hypothetical question, an astronomer from was it Belgium? No, Belgium, Netherlands. An astronomer from the Netherlands wrote him a letter, and the letter said, "Okay, there's this thing in the sky, and here's the location of it." And he pointed. Okay, so you know when you look at the sky and you use one of those astronomical instruments, you could give like an azimuth, and you could give a steepness, and then where in the. Okay, so you can like tell me where it is in the sky. So he says at midnight, here's where it was. And then the next night at midnight, here's where it was. And the next night at midnight, here's where it was. And so he gives the position of Ceres and the time at which the position was taken for many separate nights in a row. And then he was staying up really late at night because Ceres keeps advancing or declining through the sky. And eventually, Ceres was in a place where he could barely see it as the sun was about to rise. So the sun's about to come up and he says, okay, that's where it is, but I know tomorrow I won't be able to see it because I can barely see it today. I mean, I see this clear pattern of where it should be, and he knows where he could look. The problem is it'll be too bright to see Ceres because the sun will be up. So he packages all that up and zips it and sends it in a file via email to Gauss and says, Gauss, where should I look in the sky? And when should I look in the sky in that location when I want to see Ceres next? And Gauss does this sort of like straight line interpolation across the sky and extrapolates out to, well, and in a few weeks, you should see it over there at that spot at this time of night and on this day. And lo and behold, the guy who discovered Ceres looked at that spot, and that's where he found it. The method that Gauss invented is called least squares. Those are from a more mathematical and engineering background, may have heard of it referred to that way. In my discipline, we call it regression for regression to the mean, which is a term invented by Francis Galton, Charles Darwin's cousin, cool guy. Actually, he's a bit of a dick, but a different issue. And instead of regression to the mean, he called it regression to mediocrity. And so if you look up regression to the mean in Wikipedia, it might tell you it's called really regression to mediocrity. And if you look up Galton, Galton, and regression to mediocrity, you can see the explanation for how he went to France and collected heights on fathers and their sons. And from the height of the father and a scatter plot, he could predict the height of the sun quite precisely compared to just say, I don't know, ignoring the height of the father. Okay, let me ask you a question. Does it seem as though the larger the home, the more expensive it is? I see a trend. Do y'all see the trend? Do y'all see a correlation? If you see something that you'd call a correlation or a trend in the scatter plot, you're saying maybe regression is a method that I could use. With your, I don't know why age equals diameter. What was that? Okay, I forget the example there, but oh yeah, the age of a tree should depend on the diameter of the tree at breast height. That's not a data set that we have, but if you're in forestry, you've done some work in that area and you sort of measure the height of the tree about this tall up when you're standing. And then based on information you have about the age of some known trees and their diameter at breast height, you could predict the age of, well, the one you're looking at right now, but you don't want to drill a core into it to see indeed how many rings there are. That would hurt the tree perhaps, and it's got a lot of effort. So you could just tell me from a scatter plot if there's a relationship and things like a slope. And I'll say if a few assumptions hold as well, you can do a hypothesis test. I think we're going to get to those assumptions today, and in the lab we certainly do touch on them. But if there are any questions about those assumptions, A, we cover them again in chapters 8 and 9. B, it's going to be something you can ask about tomorrow. And C, not a big deal for then the exam. Okay? Any questions about that so far? Okay. So let me write out what I will call a simple linear regression model, SLRM, simple linear regression model. And maybe if I make this big, I can then draw on it more easily. And I guess because it's a sort of a greenish background, red will stand out quite nicely. So in this simple linear regression model, your Y value is your response. Can you even read that it says response? I think I maybe chose a very poor color. None of you are squawking at me now. So response, okay, I'm gonna write the other things down lower so you can see them more easily. Here is a linear trend relating Y, the response variable, to X, the explanatory variable. So that's the explanatory. And so you might think the height of a person could be X and Y could be that person's weight. So beta 0 plus beta 1 times X, that pair is the typical value of Y. For X equaling the particular that you are using. So I guess if you tell me beta 0 and beta 1 and X, I could tell you the typical value of Y, okay? But there are these other terms, or this other term epsilon, let me greenify it there. That epsilon tells me how far you are away from typical. Let's talk about an example, heights and weights of California adult males. And there's a fairly healthy data set from 1984 on the California adult males, their heights and weights, and a lot of other information about them. It's in the Health and Nutrition Examination Survey. HANES is what it's sometimes shorthand called. But if I tell you all of the heights and all of the weights of 500 randomly chosen California adult males, I would imagine a scatter plot would show a trend. And furthermore, if you knew the trend itself, that is, if you will, the trend, the true underlying trend, my color choice sucks. Okay, so let's go with black. So if you knew the true underlying trend, that's an E, trust me it is. If you knew the true real trend between X and Y, then, and let's emphasize that this is a T, damn it. So if you do the actual trend relating X to Y, you know the typical value of X. And I'm thinking, well, is there a typical height? No, I'm sorry. Is there a typical weight for any given height in California adult males? I'm thinking there is an average weight for people who are 5'6". For 5'7", there's a different average weight. 5'8", yet a different average weight. 5'9", yet a different average weight. The slope has something to do with what that average weight is as I go up from 5'6" to 5'7" to 5'8". But there is a typical weight for any given height. Yes? Yes. So what about then this epsilon term, this epsilon? That is, well, how different you are than the average person of your height. Steve, me, I am 232 pounds. I'm 5'8.5". Someone who's 5'8.5" on average would be, let's just math it easily. Let's say that should be 200 pounds. I'm 32 pounds above average. My epsilon is plus 32. For someone who's 5'8.5", they should on average weigh, say, 200 pounds. If they were only 195 pounds, their epsilon would be a -5. The epsilon tells how different you are, or each individual is, from the average true underlying trend line relationship. And if a bunch of things are true, that the epsilons all follow normal distribution, and we'll show you in the lab today, and again in chapter 8 and 9, how to check for that. But you can probably bet that it's including a Shapiro-Wilks test. And if the true average epsilon is 0, whatever the value of X is, that says linear. Admittedly, it says it really differently, but that means, second bullet point, linear trend. Third, the errors don't tend to be positive for some axes and negative for others, and they all have the same spread around the trend line. Okay, how far away are people from the average? Well, it's going to be the same for 5'6" people as for 6'2" people. Same spread around the trend should be the same, whatever the height. Then lastly, if you know that my epsilon is plus 32, that doesn't help you predict the next person in your sample's epsilon. Knowing information about one of the people in your sample and their epsilon value doesn't help you know any of the other epsilons at all. And those all sound plausible for heights and weights. And if all that's true, we can test some hypotheses about the slope. Literally, is there no relationship? Because if the slope were in fact 0, that would imply that as X changes, every time X goes up by 1 unit, the average value of Y goes up by exactly beta-1. Oh, if beta-1, the slope is 0, that means there's no relationship at all between X and Y. Or on the other hand, within this category of linear relationships that we're considering, if beta-1 is not equal to 0, that means that there is a trend. As X changes, Y changes on average. We've got, of course, a test statistic and a p-value. And if you're going to just read the p-value off of the software, which is my recommendation, you know what to conclude. Okay, I haven't shown you any data yet or how to get to there, but if you have questions now, before we move on, that'd be wonderful.
Where it says epsilon has, I think SD, is that standard deviation?
Yes.
And then equals, what's that weird little circle guy again?
Yeah, it's called sigma. And sigma in our class is a way of measuring the spread of the data points around the typical value. In this case, the typical value, which is based on the numeric value of X. In ANOVA, sigma would be the typical value of the spread around the group average.
So it'd be like the average X value?
Well, let's try a little bit differently. My epsilon is a plus 32 because I'm 32 pounds heavier than the typical person of my height. And if the sigma value was, let's just say 15, that means the typical person has a weight which is within 15 pounds of the trend line. So here's our trend line. Within 15 pounds of that trend line is where we find the heights. Let's actually look at this guy in terms of the scatter plot one more time, and maybe I'll identify the way you could see approximately the value of sigma. Here's my scatter plot, and I'm thinking I could just bracket the bulk of homes with a trend line. Now I'm gonna just draw in a trend line. It might not be the perfect one, the best one of all possible trend lines, but that looks like it approximately tells me the average value of y for any given x. And I'm looking at 4 of you, and none of you are shaking your head saying, well, that looks horribly wrong. So good. And I'm going to say, well, plus or minus about how much? I'm thinking the bulk of the values are sort of in that range. Yeah. And if I go up 1, 2 standard deviations, sigma up and another sigma up, sigma down and another sigma down, sigma and sigma, that should cover or capture about 95% of the actual data values. So it's a measure of spread of the data values around the trend line. How much variability is in their prices for homes that are 2,000 square feet? Or how much variability is there in prices of homes that are 1,400 square feet? So Caroline, does that get
That
towards-
makes more sense.
Yeah.
Then the one other question is, why is it why do we do 2 up and 2 down there?
Yeah, because in a stat class, if you go up and down 2 standard deviations, that captures about 95% of the values.
Okay.
If you go up and down just 1 standard deviation, that would only capture about 2/3 of the values. And it seems easier to draw, hey, that captures nearly all, or 95%, than exactly 2/3. So that's why we usually like that plus or minus. And also it feels better to have 95% wins than only 2/3.
Sounds good. Thank you.
So that's your friend sigma. And there's a trend line there, and maybe I'll just label it here as beta 0 plus beta 1 times x. Here are your x values, and here is your y, and here is, if you will, the average y for this x, the one that we give. So if it was a, say, let's go with a 4,000 square foot home, you'd expect a sales price about $550,000 based on this graph. Okay, so I'm going to sort of do a screenshot there in case any of you asked me to upload those, and I'm going to clear it and flop back over here. Any other questions about this list here? Okay, so what I want to do is get after, I'm going to skip over the regression assumptions for now. That's something it's covered in the lab, but is not emphasized on the first exam. I do want to talk about a t-test for the slope, the standard error of the components, and this relationship strength, if you will. And maybe we'll get down to R squared. So this is where we're going in the next 10 to 15 minutes. Okay. So a t-test. You remember the t-statistic before had the difference of 2 sample means divided through by standard error. Okay. Our hypothesis test here is with a null hypothesis that there is no relationship at all between the explanatory and response variables versus the alternative. There is a relationship. Our test statistic is, if you will, the sample slope divided through by the standard error, and that standard error tells us how close our sample slope is likely to be to the true underlying population slope. How close is our estimate, B1, likely to be to the truth, beta 1? There is a truth out there. I don't know what it is, but I've got an estimate of the slope based on my data set. Okay? Our standard error tells us how close our sample slope is likely to be to the slope of the population. And let's get after this equation or these three concepts with three pairs of pictures. And I'm going to say, imagine going to the optometrist. Now, I'm looking around the room here, and I'm not seeing every one of you wearing glasses, but I know that some of you do. So you've been to the optometrist office, and at one point in time in that experience, if you need to be fit for glasses, the guy sort of shows you the thing that you're looking at. It's like A's and B's and J's and stuff. And they say, okay, can you see this? And you say, okay, pretty well. And then they sort of make a change in the setting and then say, would you rather number 1 or number 2? And you say, oh, well, number 2 looks a whole lot better. So you say number 2 is better. And then they make it another adjustment, and it continue to sort of check with you on revising what allows you to see it 20 feet away most clearly. Or if you are farsighted, what allows you to see up close most clearly, okay? So they basically want to say, let's measure your eyeballs in terms of the amount of correction you need. And they consistently say, would you rather this or that? So let's tackle one of these questions that I want to have. Would you rather have more data or less? So I'm going to draw two graphs for you. And
More.
they're an attempt. Oh, yeah, that's the obvious answer. But if I showed you where the bulk of the values are in the population by drawing an ellipse, or approximately an ellipse, and with the approximate ellipse, I'm going to show you, you have 6 data points. Oh, hold on, 5 data points. Or would you rather have 38? In which situation can you feel most comfortable saying our trend line in the data set is reflecting the true population trend line? I would rather have more data than less, yeah? Okay, so that's why N matters. So let's clear that and get back to our friend. Okay, there we go, back to our friend. N matters because if it is in the denominator, the larger the sample size, the smaller the standard error. Let's say that again, but a little bit differently. The larger the sample size, the more precisely our estimate will be following the true underlying population slope. So that's a win. We want N big. What about this a second term? And I'm going to go with SE right up here as the second term. And let's get back into our compare and contrast. Would you rather a situation where you, in the population, you have, let's say, very little spread around the trend line or a lot of spread around the true population trend? Would you rather say, let's go with 8 data points? Would you rather have 1, 2, 3, 4, 5, 6, 7, 8, or 1, 2, 3, 4, 5, 6, 7, 8? Would you feel, shoot, it's not about feelings. Is it likely that one of these will be able to more precisely tell you the underlying trend relationship than the other? Which one's going to be better, upstairs or downstairs?
The upstairs one?
Yeah, why?
Because they're more closely on a line, like in alignment.
Thing. Yeah, no matter where the data points are in this upper graph, no matter where they are, if they're in that very tight, narrow bubble with a slope of 5, then for any 8 data points, we're going to have a fairly precise understanding of the XY relationship. But in the second graph, which is not as good, so maybe I'll make it an X, ooh, bad, ooh. The 8 data points, they could, instead of those shown here, let's show you an alternative possibility in green. Maybe you'll have something like that, which would even cause you to say, oh, look, the trend is negative. And that could easily happen if you have a lot of spread in the population around the XY relationship. So spread, the less spread around the true underlying trend, the smaller the value of sigma, the more precisely you know the truth. SE the smaller SE is, the more precision you have. Now, a couple of ways to think about S and E. That's the square root of mean square error in your regression output. Okay, and you already seen mean square error. Take the root of that. You could call it the standard deviation of the residuals. And it's just a way of measuring how much vertical spread there is around the trend line. Last one, standard deviation of the X's. So let's again make some sense out of this with a picture. And let's go with 2 choices, and I'll go with the one on the right and the one on the left. I noticed as I said that, I said the one on the right when I was drawing the one on the left, but y'all figured it out, okay? So different spread. Okay, so if we want to estimate a height-weight relationship in adult males, and if that is the true population trend line, would you rather see a bunch of people that are 5 foot, say 8 to 5'9" as your sample? Let's go with 7 data points. Or would you rather have people who are widely varied in terms of their heights? Would you be able to more easily spot a trend with precision with a lot of short people and a lot of tall people than everyone in approximately that same height range of 5'8" to 5'9"? Yeah. In fact, some people would even say, if you get to pick your X values, why don't you even go with some 4 people that are really short, or 3 people that are really short, 3 that are really tall, and then 1 sort of in the middle. If you get to pick the values X, you might be able to even spread apart further those X's. The standard deviation of the X's, the spread in the X's around the average X bar right here, will tell you how close your slope should be to the population trend line's slope. So let's go ahead and clear that and not spot in our equation where S sub X is. Oh, it's in the denominator. The more widely spread the data points are out in the X's, X lower and X higher range, the higher that value for S sub X, the smaller the standard error will be. So you can see why all 3 of those terms at least would be related to a measure of precision for the slope. Let me get after our example in greater depth here. Again, these are the heights and the heights, the size of the home, and then the price of that home. So let's go with the data here. Here's our scatter plot, the XY relationship, and maybe I'll make it smaller. Actually, I like it like that. Yeah. Okay, so I can still see a trend line, but as you spot, the software will make a graph for you, but I don't see slopes and intercepts or anything like that. If you, however, say, oh, fit that line, add that line in the scatter plot. Again, here is your way of changing what's already been done by the software. Let's add a line. So it's going to draw in that trend line. And notice that it draws in the trend line, 30. We don't really have an X of 0 here. Maybe we could drag it over if we wanted until we can see an X of 0. And because we don't have a Y of 0, if you really want to see that Y of 0 location, we could again make sure that the origin is down there in the lower left corner. You don't need to do that, but some people forget that the intercept and slope aren't so perfectly shown unless you sort of adjust that. And maybe let me make this graph a little bit differently shaped so we can see its geometry a little bit better. So I could show you the XY relationship. And so for every 1 unit up, we go in 100 square feet. So each time you increase the size of a home by 100 square feet, and basically think this, okay, you're living in a home, it's a rental home somewhere over near Patricia or something. And the owner says, okay, I'm going to just add another bedroom off to the back, add a 100 square feet, and knock down one wall and make another 10 foot by 10 foot room. Okay, you can add the room to the house. How much would the value or the sales price of the home increase from adding one 100 square foot room? Because, I don't know, how else do you get an extra 100 square feet? Just add in one room maybe, okay? Our trend line shown here, the linear fit, says the typical price in thousands of dollars is $93,000 plus then $9.88 for every extra 100 square feet. So $9.88,000. That's working $10,000 per 100 square feet. If you go up from a 1,400 square foot home to a 1,500 square foot home, we're saying they cost about $10,000 more. For each 1 unit in X up that you go, for each extra 100 square feet, how much is the price in change in thousands of dollars? Okay, so here's my trend line. Yay. You can spot the trend line in 2 different locations. The equation, here's your intercept, your estimated intercept, your estimated slope of 0.8827,464,000. You can spot here down again in parameter estimates. And we'll get used to seeing a lot of things called parameter estimates. Maybe yeah, we can see that down at the bottom. This says $93,000 plus $9.88,000 for every extra 100 square feet. So I can see an estimate and a standard error. And somehow we have a standard error and an estimate. That ratio, sometimes called a T ratio, gives me a p-value. In this case, it's less than 0.0001, which tells me if there is no relationship at all between the size of a home and then the price of a home. With a data set like we have here, 320 data points, almost never would we see a slope this steep. Like basically, we shouldn't have seen what we did see in these data if the null hypothesis were true. What we see in these data should not have been if there really was no trend. If really the trend line is flat, by luck alone with 300 some data points, I should not have seen it this steep. Any questions on that so far?
I had a question. Are we ever going to use the analysis of variance p-value? Like, what is that for in this case?
Perfect question, because that's what I want to talk about next. The analysis of variance p-value in this regression context is, oddly enough, exactly the same here. And this F ratio, for reasons that I'm going to ignore for now, but I'd be happy to explain later in office hours before the midterm or in class afterwards, meaning it's not really important and is probably not something you should focus on before the test. This slope test squared should be equal to that F ratio exactly. And so the p-value also should be exactly the same. So the analysis of variance, you could look there instead of down here to see if there is a relationship or not. And so for many students in this class, because our book says, yeah, just look at the ANOVA F table, you would say, is there a relationship between this explanatory and this response? The answer is, heck yes, there seems to be. And for this situation with one slope, and that's it, these 2 values will always be identical because they're testing the exact same thing. In class next week, we will see indeed that that will not always be the case. And the upstairs analysis of variance hypothesis test tackles a different question than the slope test, but that's for next week. One other thing I would want to draw your attention to, and that is the summary of fit. And I'm going to sort of draw that down, maybe make that smaller. So the summary of the fit, we've got a couple numbers that you should pay attention to. One is the sample size, the number of data points, the number of observations, 321. The root mean square error, oh, that's 55. Notice that in the ANOVA part, the mean square error, yeah, the square root of 3057, you might not remember that is exactly 55, but yes, it is. This root mean square error is a measure of vertical spread of the data around that trend line. Okay, I'm gonna see if I can draw a picture for you approximately. I don't want to do that now. It's with the next method that I'm going to be able to more easily do that. Okay, so so just say our trend line. Okay, if we took the trend line and went up $55,000, slide the whole thing up, and another 55,000, slide it up again. We got one line that's 110,000 higher, and another that's 110,000 lower. Maybe I should just even try to draw these in blue. Minus 2 times RMSE and plus 2 times RMSE. That range of values should have about 95% of the data. Okay, so it tells how widely around our trend line is our data set. One last number that I'll emphasize more tomorrow, but it's called R squared. Many of your faculty members are more in love with R squared than they should be. I'll just say R squared is a measure of what proportion of the vertical variability of the data could be considered explained by the X variable. We can explain 47% of the variability in prices based on just the variability in home sizes. And that's probably good for now. And crap, I went over by a minute. I apologize. I need to stop now because you might have somewhere else to be, and I don't want to overdo it because that's way too much stuff. But the lab between now and Wednesday at the beginning of class probably be good to work on that, because thorough understanding of this lab on regression will allow us to then move forward in concept. So I'm happy with it. I love the lab. It's a great lab, and I think you should tackle it. But if you don't love it, come Wednesday at 4 o'clock, definitely ask before we move forward. So a good place to stop to share, and I will stop the recording shortly. But are there any questions before I stop the recording? Okay, then.